So what we've had a look at is dehydrating copper sulfate. So the hydrated salt is blue, and when we dehydrate it, it turned white and went more like a powder, so it wasn't so shiny. Not all dehydration reactions are so easy to see that they've been completed. Okay, this one was easy because it changed colour. Another way we could have checked it is to weigh what we had to start with, heat it, weigh it again, heat it some more, weigh it again. Once the mass doesn't decrease anymore, then we know that we've driven off all of the water. And this is showing the balanced equation for us dehydrating the copper sulfate crystals, where they go from blue to white. Now we know that there's 5 water molecules in for every copper sulfate in the crystals, because it said that on the container. All right, but let's pretend we didn't know it. The only way that we can find this information out is to use the mass. So it's what we call gravimetric analysis. So what I'm going to go through with you quickly is, let's say that we did record the mass of what we were working with. Let's see if we can work out, are there indeed 5 waters within every copper sulfate. So the data I've got here is, let's say we started with 18.9 grams of our hydrated salt. Then what we did is we heated it, and we found that it dropped to 12.1 grams. And we heated it again, and it stayed at 12.1 grams. And we heated it again, and it stayed at 12.1 grams. So we know, we're pretty confident we've driven off all of the water that we could have. Okay, it's changed colour, it's not changing mass at all, so we're pretty confident we've got rid of it all. Okay. Given these 2 bits of information, what else can I find out?
The weight of the water molecules.
Fantastic. How do I do that?
Minus 1 to the other.
Fantastic. Conservation of mass. So we're going to go that minus that equals that, which is 6.8 grams. Okay. Now, none of my columns have got 2 things that I know yet. So what I need to do is make it so that I can solve some of these other numbers. Okay. The nice thing is that we're given a periodic table. So with a periodic table, we can find their molar mass, because we know the atomic mass of everything in them. Water is a good one just to know off by heart. 2 hydrogens, so 2 times 1, and oxygen, which is 16. So it's good to know that water is 18. Particularly as with gravimetric analysis, we're talking about driving off water all the time. Good number to remember off by heart. Okay. If we work through this, 1 copper, 1 sulfur, and 4 oxygens, we should end up with 159.6. Okay. So now that I know these 2 numbers, I can actually find out the amount of each of them that were left over. One that was driven away as steam, and one that was sitting there as a white powder or white crystal in my crucible. Okay, so I do this by the same way as we did with our other balanced equations, going n equals little m over big M. Okay, so I need to go 6.8 over 18, which is, if we do that, 0.37777, I think. So 0.38. Then I do the same thing for this one here, and I get an even tinier number, which I'd hope for. 0.07, I think it's 55555 from memory. Okay, so we'll round that off to 0.76. Well, according to the equation, how many of these should there be? 1. Okay, so I need to get that to 1. How do you turn that number into 1? Just maths.
1 divided by 0.
1 divided by it, we'll still end up with that number there. Well, actually, no, it'll be a big, really big number. I'll ask it a different way. What's any number divided by itself? 1. Okay, so if I divide this by...
Does it cancel each other out though if you divide it by itself?
Yep. to 1. If we subtract it, it'd be 0, but we're talking about dividing. So if I divide this by 0.076, what will it become? 1. Okay, so what we do is exactly that. If I'm dividing this by that number, I have to do the same thing to the other one, because this is my multiplication factor, as it were. So if I do this one becomes a 1, and this one here, I haven't done on my calculator yet. Here's where I hope that it works. 0.38 divided by 0.076 is 5. Okay? Now I know that x is 5. And x is 5 in both places. Okay, so let's go through that process again really quickly for you. The first thing is I've weighed what I start with. But I don't know its formula yet. I don't know its formula. I might be able to guess it, but I don't know its formula. It's got an x in it. I don't know.
You'd be given that.
So I'm not going to give you the formula of the hydrated salt.
Right, okay.
Or I'm going to ask you to confirm it, to prove it.
Okay.
So to find x. Yeah, good question. But I do know the mass of it. And I know what it's going to break up into. It's going to break up into x moles of water and 1 mole of the anhydrous salt. I do know the mass of what's left in the crucible. Okay? Which means I can find the mass of the steam that was driven off by doing a simple subtraction. Then I find my molar masses for these two, because even though that's x moles, it's still 18 for water. Okay? Then I can use N over M to find my amount for each of them. I then divide by the amount of this one, because the equation says there's only one of them. And that tells me the ratio, 1 to 5, or 1 to 2, or 1 to 10, or 1 to 7, or whatever. Because you're not going to have fractions of them, round them off to the nearest number. So if you got 4.1, you'd say it's 4. If you got 4.9, you'd say it's 5. That sort of thing. If you get 4.5, you probably have made a mistake with your experiment. Okay, to be honest. Probably not with your maths, it's probably a mistake with your experiment. You didn't heat it long enough, or some of the crystal caught fire, maybe it's one that can burn. Okay, carbonates are typical for that. Okay, so try not to use carbonates. So that's what we call gravimetric analysis. It's using our idea of a balanced equation. It's using our idea of that NMM thing. It's using the idea of conservation of mass to be able to find out what the formula is of a hydrated salt.